started the live telecast. Fine. So we are doing today heaps. So what are heaps? So essentially a heap is also a tree, right? Which means, just for your reference, it is something like this. You have something like a root node or a root, and then you will have it will have some children, could be 2 children or 3 children, doesn't, it depends on your structure, right? So this is a heap if it follows a heap invariant property. So this property is called heap invariant. Just like you remember BST invariant, right? That was a different property, but this is a heap invariant. This is a different property. What is this property? The heap invariant says that your parent is always less than child, right? This is called a min heap. This is called a min heap. Or parent is greater than the child. This is a max heap. They are both equivalent, right? If you can convert min heap into a max heap, and so basically we will be working with only min heaps, and I will be writing all the algorithms, codes, etc., everything for min heap, which means your parent is always smaller than the child. So let's say if you have here, let's say 2, then this will be always, actually this could be less than or equal to child. Equal to, you can, if you are allowing repetitions, then equality can also come. For example, if you're allowing, if I don't allow repetitions, then this will be either 3 or 4 or something. Let's say 5. This will be, let's say 4, and this will be something larger. It cannot be smaller. Say 9. Let's say 8. Let's say this is 3. No, 10. And this will be 20. Right. So this satisfies the heap invariant. So basically you have a smaller element, then so the child is always greater than the parent. That is the heap invariant, which defines a heap. Right? So heap invariant, so basically heap is a tree which satisfies the heap invariant. Is that all right? Okay. So what is the benefit of using a heap? One of the benefits which we have seen in the past is in the priority list, right? Oh, sorry, yeah, in the priority queue. So what happens in a priority queue? It is a queue, but whenever you pop or whenever you dequeue something, so for example, priority queue. So what is a priority queue? It's like a hospital queue. Here you have some, from here you dequeue things, and here you enqueue, right? And but there is also a priority score. Let's say there is this person comes in, and this person has a priority score of, let's say 1. Then this person comes in. This person has a priority score of 5. Then when a new person enters, let's say this person has a priority score of 2, then it won't enter here. It will directly land up here. So this person will directly land up here. Or in other words, you can say this person enters here, but then there is again a sorting, and number 2 will go here. So this thing can be implemented with the help of a heap, right? So this is the heap. You always dequeue from the top. Always dequeue this one, and then do the shuffling so that everything is again arranged in the proper sorted order. Right? So the advantage of using a heap is that this sorting, this shuffling which we are doing, or not shuffling, it should be called the sorting. This sorting which we are doing, or this rearrangement to make the heap invariant, this is very fast. Right? So the advantage of heap basically, so whenever enqueuing and dequeuing in the priority queue, or in other words, adding or removing elements in a okay. Now tell me, if I implement a priority queue using a list, what is the complexity of adding or enqueuing? So if I use a with let's say simply a list, could be linked list or just a list. What is the complexity of enqueue? Pardon? N. Yes, very good. N is the number of elements present in the queue. When a new element is added, that enqueuing will be of order of N. Dequeuing can be fast, let's say order 1. If it is already sorted, then you are just dequeuing. This could be fast in that case. Okay. But the overall process of enqueuing and dequeuing, the overall process has the complexity On, right? Now let's see if I do it with the heap. What is the complexity for adding and removing elements? What is the complexity here?
Log in.
Yes. So you see, if I add a new element, let's say 1, how that element will be added, I don't have to compare it with each and every entry. I have to just compare it along a path. I will tell you how the algorithm is, but it turns out to be O log n. Here log to the base 2, because anyways, it doesn't matter. Even if you take log e, then it's just a constant, so it doesn't matter. So, okay. I will discuss this adding and removing algorithm means in a moment. But before that, let me define some terminology, some terms. So all of you know what is binary heap? Binary heap means, yeah, so number of children is always less than or equal to 2, right? For every node, number of children is less than or equal to 2. That is a binary heap. Now, what is a complete binary heap? This also you have studied before. Complete binary heap. Yes?
All levels are completely filled except the last level.
Yes. All levels are completely filled. And last level can be unfilled. But all nodes are in the left. All nodes are at left. Right? So, for example, if I say this tree, this tree is a complete binary heap, right? Whereas, so this is complete binary heap. But this one is not. Why? Because this one is missing, right? So to make a complete binary heap out of this, if I transform it like this, then this is a complete binary heap, right? Because all my last level nodes should be at the left. Okay. So this is a complete binary heap. These are just two terms. And now we will be, I will be discussing binary heap and a complete binary heap. Means I'll be discussing mostly about a complete binary heap. Means we are mostly interested in complete binary heaps. Even the priority queue, it can be implemented as a complete binary heap, and it's very efficient and very easy to understand. Okay, let's look at the some properties of a complete binary heap. Okay, let's say I will just draw a heap here so that okay, one more. Okay, you can make it larger. Okay, let me put some node indices so that this will be helpful for you to answer some of the questions. Okay, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let me just, these are two extra nodes I have to take. 16. Okay, first question is this a complete binary heap? Is this a complete binary heap?
Yes, sir.
Okay, good. Yes, it is a complete binary heap because all the last level is unfilled, but all the nodes are towards the left. How many levels are there in this heap?
Four.
5.
Okay, so okay, let me define what are levels. So this is one level. This is L equal to 0. This is L equal to 1. L equal to 2. L equal to 3, and this one is L equal to 4. So total 1, 2, 3, 4, 5 levels are there, where 4 levels are completely filled and the 4th level is unfilled, but all the nodes are at the left. Okay, so total 5 levels are there here. Okay, now if I ask you if it is a complete binary heap, what is the maximum number of nodes at level L? Maximum number of nodes at level L is equal to what?
2 raised to the power L.
2 raised to the power L, yes. So you can verify it. You can say this is L equal to 0. So 2 to the power 0, 1, 2 to the power 1, 2, 4, 8, etc. Okay. Now tell me maximum number of nodes for a complete binary heap with capital L levels. Maximum number of nodes for L levels. L level complete binary heap. There are total capital L levels in the heap. Then what is the maximum number of nodes that can come? What is the maximum number of nodes that can come?
2 raised to the power capital L minus 1.
2 to the power capital L minus 1. Minus 1 or minus 1?
No, sir. Whole minus 1.
Okay. How do you decide this?
So simple geometric progression addition.
Yes, very good. It's simply a GP. It is 1 plus, so basically 2 to the power 0 plus 2 to the power 1 plus so on plus 2 to the power L minus 1, right? Which is equal to, this is a GP. So the sum of a GP is 2 to the power number of terms. There are total L terms minus 1 upon 2 minus 1. Simple GP. Okay. Now another minimum number of nodes for L level CBH. What is the minimum number of nodes?
Two raised to L minus 1.
2 raised to the power L minus 1. Whole minus 1.
L minus 1. L.
Whole minus 1.
Okay. So if you take minus 1, this will be only up till level L minus 1. So plus 1 to make it. So 2 to the power L minus 1.
Okay.
Okay. Now, if the number of nodes is given, if the number of nodes in a CBH is small n, then what is the number of completely filled levels for total n nodes, number of completely filled levels? If there are total n nodes, how many levels are completely filled? Yes.
Floor of log 2n.
Floor of
Log
log to the base 2 n.
n.
Do you agree with this? Okay, let's derive number of completely filled levels. If the number of completely filled levels is L, number of completely filled levels is, let's say, L minus 1, you can say. Then the number of nodes here will be 2 to the power L minus 1, right? This number will be basically less than or equal to n, right? Now you take it as n plus 1. I'm doing some mistake, just a moment. 2 to the power, I did a mistake. It's maximum number of nodes at level L. Maximum number of nodes for an L level CBH is 2 to the power L minus 1 and plus 1 to the power L minus 1. So basically this term has to be less than n always, right? It cannot be equal to n, right? This term let's find out. We'll verify it anyways. So this comes out to be to the power L minus 1 is less than n plus 1. So let's take a log to the base 2 n plus 1. So here L is less than plus 1. So basically, if you take now a floor of this, then your L will be that, right? Let me verify this. Let's verify it. Okay, let's take my small n to be 14, or let's take it 15. So this is a case when let's take my n is equal to 15. Then what is my capital L? Capital L will be log to the base 2 16 lower of that, which comes out to be how much? 2 to the power 4 is 16, so 4, right? So which is 1 2 3 4. Yeah, this is correct answer. It's 4. Let's take n equal to exactly 14. Let's take n equal to 14. Then my capital L will be equal to log 2 15, right? Log 2 15 will be 3 point something, right? Because 2 to the power 4 is 16, so it will be 3 point something. So which means my L comes out to be 3, which is not correct. Okay, this is a mistake. This is not 14, this is 15 actually. This is the numbering starts from 0, but total number is, okay, I'm sorry. So if n is 15, then it is L equal to 3. Okay, when L is 14, then number of completely filled levels is actually 3 only. So this formula is correct. This formula is correct. So this is the formula. Okay, yeah, log 2 n plus 1. Right? Okay. Next question is, now the next question is important. When there are total n nodes present in the CBH, where will the next node go? If I add another node, which level will it go to? We'll say next node goes to level equal to, which level will the next node go now? Yeah. The next node goes to which level?
It should depend on node value, right? Because heap is sorted.
No, means okay. Which means, let's say we're not talking about the sorting yet. It's just that, okay, if I add a new node, it will go to which level basically.
Okay, then this number completely filled level plus 1 level.
Yeah. Yes. So basically this thing plus 1. Okay. Yeah. And once we add this node, then we will do the sorting thing. Okay. Now next question is a little tricky. If I have okay, at the lth level, what are the node indices? At the lth level, what are the node indices? Right? Let's say this is L equal to 2, the node indices are from 3 to 6. At L equal to 3, the node indices are from 7 to 14. So what are the node indices for any general level L? Yes?
2 L minus 2.
2 to the power L minus 2.
No.
Minus 2. Pardon?
Yes, minus 2.
Here,
Not yeah, here, yes.
okay.
Up to 2 raised to L plus 1 minus 2.
2 to the power L
Plus 1
plus 1
minus 2.
Okay, let's verify it. Let's take L equal to 0. For L equal to 0, this is -1.
Okay, sir.
For L equal to 0, this becomes -1 to 1.
So
For
it
L
should be
equal to
2 power
1.
L.
Pardon?
So it should be 2 power L minus 1 to the limit.
Now it, okay, sorry. Let me get the green one. Now it is 0 to 1. Okay, let's try for L equal to 1. L equal to 1, then this goes from L equal to 1. 1, 2. Oh, for 0, it was 0, no? 0 to 0. And then for L equal to 1, it goes from 1 to 2 to the power 2 is 4. 4 minus 2 is 2. 1 to 2. Yeah, this makes sense. This one is looking better. For L equal to, and instead of using this, I'll say 2. Because this one is also included. This is not the Python numbering where you don't include the last index. Here, this is included. Okay, L equal to 2, it goes from 2 to the power 2 is 4 minus 1, 3. 3 to 2 to the power 2 plus 1 to the power 3 is 8. 8 minus 2 is 6. Yeah, this is giving correct answers. How did you derive it basically? First of all, you find out at L minus 1 what is the index of the last thing, right? So you can find it from here. Number of nodes for an L level CBH. So you go to L minus 1, right? The number of nodes comes out to be 2 to the power L minus 1 minus 1, right? Oh, okay. L is the number of levels, but small l is the index, and indexing starts from 0. That's why to the power small l minus 1, because again the node indices start from 0. That's why there is a. So we have to be careful about indices and the total number of something. But this is about indices, so that's why you are finding 0 is extra here. Okay, so that's how, and then you essentially multiply this thing with 2 because. Okay. Fine, this is done. Yeah, these were some exercises which you will need to implement your algorithms for the complete binary heap. Now let's come to the algorithms. Anybody has any questions here? I think this was pretty straightforward, right? Just a GP and related concepts, right? Now let's come to the first algorithm.
Excuse me.
Pardon?
Excuse me, sir. Sir, can you one more time explain the number of completely filled level property?
Number of
Completely filled for n node. Yeah. That formula floor of log to log of n minus n plus 1 to the base 2. How did it can you explain that?
Okay, so number of completely filled levels when you are given that there are n nodes available. So if there are n nodes available, then what is the okay, if there are n nodes available, let's say assume there are capital L completely filled levels, or there are capital L levels and L minus 1 are completely filled. Let's assume, right? Capital L minus 1 completely filled levels, right? Where capital L is the total number of levels in the heap. Okay, let me write it down. Let L levels, comma, L minus 1 are completely filled. Okay, L minus 1 are completely filled. So this means 2 to the power L minus 1 minus 1 Now this term should be less than small n, right? Total number of nodes in this basically up to L minus 1 levels, this total number should be always less than n. It cannot be even equal to n, because if it is equal to n, then your tree does not have L levels, rather it will have L minus 1 levels. So we have assumed that there are L levels in the tree. So therefore, up till L minus 1, number of nodes will be less than n always. Now there is just some rearrangement required. I took the one that side, and finally you get capital L is less than this number, right? This means my capital L will be basically this number. Means I think that is very clear now, right? L will be equal to the
log of n plus 1 to the base.
load of this. Yes. All right.
Yes, sir.
Okay. Thank you. Let's go to now we'll discuss some algorithms. First, we are going to discuss about adding an element to a heap. Let's take a heap which we have already drawn somewhere. Yeah, let's this one. Let's take this one. I want to add a new element to it. Let's say I say, you can say, I will, okay, I will use the word add and remove. Let's say add a new element, let's say 1. Right? So basically, I'm writing it like this, but when you will have your Python code, you will say class heap, let's say capital H heap. And then here there will be a function called define add. And here you will be giving the value, self comma value. And then here you will say some heap h dot add 1, right? So I'm just writing in short, it's just function add. If I add a new value 1, how will I add to this complete binary heap? So the solution is you add 1 here at the immediately next level, whichever is available. So use this formula to complete. The next node goes to which level, and then what is that new node index you can compute. So this is the node index, right? Let me add it here. So 1 goes here, right? But this does not satisfy the heap invariant, right? Because 1 is a small value. It should be not below 9, right? So the next step will be called bubble up. It is just like you have water, and in the water, if you add there are heavy things and there are light things, right? If you put a heavier thing like stone will sink down. And if you add a heavy thing like, if you add a light thing like a air bubble, air pocket, that will bubble up. So this 1 is a lighter thing, right? It is a min heap, so it should be at the top. So this will bubble up. So what will happen is you will compare it with its parent. If the parent is large, the parent will sink down and this will go up. So basically the parent will come here 9 and 1 will come here. And then what will happen? Then again it has come up here. Okay, now again compare with the parent. Now the parent is again heavier, or it's larger. So parent will sink down and this will bubble up. So instead of 1 here, 5 comes here and 1 goes here. Now again it will compare with the parent. Now the parent is lighter or the heavier and son or the child is lighter. So you again bubble up, 2 comes here and 1 goes here. So finally your tree looks like this, or your heap looks like this. You have 1. Let me try it with the, you get 1, here you get 2, here you get 5, and here you get 9. The rest all things are same. Right? So in this way, I have now see, is this a heap now?
Yes, sir.
Yes.
It is a heap. It follows the heap invariant. And is it a completely filled binary heap? Yes, it is a complete binary heap. So this is the adding algorithm. How do you add a new element anywhere? Right. I can give another example. Let's say if I ask you on this, can you add a new, let's say add 9.
Hello, sir.
9 is already there, huh?
If we want to add, suppose 0 in this structure,
Yeah.
this heap, then are we going to add this like before bubbling up? Are we going to add this after 9, below 9, or the right child of 5?
Yeah, it will be the sibling of 9 because we want to maintain the complete binary heap property also. So the next node will appear here. Let's do it. Let's take an example. Tell a number which you want to add. Let's say add 25. So what will happen? You will add it here. And that's it. It stays here because it is already heavier than the parent or more than the parent. So it will stay at the bottom only. It won't bubble up. Right?
Add 3, sir.
Okay, let's do that. So on top of it, if we are doing now add 3. So what will happen? It will come here. Next available node is this 3. But now compare with the parent. Okay. Let me see if I can write down all the steps. Okay. Let me write it down here. So first of all, or create a new node basically. Create a new node with that value. Then you have to do bubble up. Now what is bubble up? Bubble up means compare with the parent and if it is large, if it is large, stay there. And if it is small, swap with the parent, right? And do this until, okay, stay and break. And you can make this a while loop. It's an infinite while loop. It will break only when your child is large. Right? Okay. Now let's add 3. Okay. We have added 3. Now what do I need to do? I need to compare with the parent. If I compare with the parent, it is small, it is lighter. So 8 comes here, 3 goes here. Again, compare with the parent. it is heavier. So that's it. The loop will break and I will stay here only. So that's the final tree which I get. Let's redraw it. And 8. All right. That's the final heap I get. Any questions on this? I think it's quite straightforward now. Now, when you're implementing this, you need to be able to access the parent also. And not only let's say given a node, not only it should point to the children, but you should also be able to find the parent in O1 very fast. So basically you have to implement the tree in a slightly different way so that you can quickly access the parent, right? Because in the previous implementations, finding the parent was difficult. But here I need to find the parent also very quickly. Okay. Now let's define the next operation called removing the element, right? Dequeuing, right? So enqueuing is what you have learned. Now how about removing an element? It could also be called dequeuing or polling. How do we do that? Let's take a binary heap, complete binary heap. Now I want to remove an element. Let's say first I will consider the case when I want to remove the element from the root. So number 1, from root. How do I remove the element from the root? Let's say I say dequeuing, or simply remove, or as you say, dequeue. So what will it dequeue? This node will go away, right? So this node will go away. But if you remove this node, then your heap property will be, heap invariant will be not maintained, and it will also not be a tree anymore because root is gone. So how will you maintain the heap invariant?
Sir, we can give that node a very high value and let it sing, and when it reaches the last level, we can remove it.
No, but you can't remove the value, cannot change, no?
Sir, what we can do is give the lighter child of that root, make the lighter child as the root node, and next proceed up to the lighter node. Again, assign the lighter node to that place. Just like we can assign 2 in the place of 1, then 3 in place of 2, and 8 will go in the place of 3. It's
Yeah, but the problem there will be, let's say, if you remove 1, 2 comes here, 3 goes there, 8 goes there. Let's say if there is another node present here. I'm sorry. Let's say there is another node present here, maybe which has a large value, maybe 14. Then what will happen here is, okay, you will move 8, means you will remove 1, 2 will go up, 3 will go up, 8 will go up, but then this is no longer a complete binary heap, because your 8 is removed, and here is a void. Then you have to again move this 14 here and remove this, right? But what if there is also underneath many things? So at some point of time, you may be stuck. Yeah, but your intuition is good. Your intuition is correct that if we remove one, something has to substitute here. But that something, it should come from the last node only, right? So why not we put the last node on the top and let it sync? So first we preserve the shape of the tree or the architecture of the tree, and then we rearrange the nodes by swapping them, right? So what are the steps? Number one, that when for dequeuing, first of all, okay, remove this one, take it out, but take the last node and move it here, right? Remove one, but take the last node and move it here. So what happens is here we get 14, and this node gets removed. In this total, everything is destroyed. It is removed. Now you let this sink down, right? And what is sinking? Let's say I swap 14 with 2. 2 will come on top, 14 will go here, right? But the question is, which one should I swap with? Should I swap with 2 or should I swap with 4?
Swap with a smaller one.
With a smaller one, yes. Because if I swap with 4, then the 4 is a heavier thing which comes on top of 2. And then again here, you have to do more operations. So it won't be very efficient. So you swap with the smaller one. Okay, so you swap with the smaller one. 14 goes away, basically gets swapped with 2. So here you get 14, here you get 2. Then again, you have to see sinking down. Which one should I replace it with? With 3, right? 3 is smaller one. So here we get 14, here we get 3. Then again, this will sink down. 14, 8, it gets swapped. 14 comes here. That's it. So we get finally this binary heap, which is actually maintaining all the properties. It is a complete binary heap. Okay. So what are the steps involved? Let's write them down. First of all, remove the node. Remove the root and put the last node there. And then you have to do sinking down. The root will sink down. So what does that mean? It means the algorithm is something like this. Compare with the children, and whichever child is small, you swap with the child. So if smallest child is less than this node, then swap. Or else the smallest child here is not small, even it's larger, then you can stop there, right? And break. And this you can do until you converge. Right? Smallest child is less than this particular node, then you swap the two. And if it is larger than, then you can stop. Okay. That's it. So you understood removing an element from the root. So basically this first step is to maintain the completeness property. And this step is to maintain the heap invariant. Right? So this is to maintain the structure and this is to maintain the heap invariant property. Okay. Now, okay, this was about removing from the root, which is the standard way. Whenever you do DQ, it will always remove from the root only, right? Okay, just a quick question. If I want to implement a priority queue with a heap, what are these numbers? Is this the information or is this the value or the priority index?
Priority index.
Priority index, right? So which means your every node will contain a priority index as well as the value, the actual data which that node is holding, right? The actual person who is having that priority, right? So your node has to save both the things. Okay. Anyways, that depends on your problem and implementation. So you implement it properly. Now let's come to if I ask you to remove some element from anywhere in the heap. If I say, oh, do you have number 4? If you have it, then can you please remove it? So what you have to do is you have to now search the entire binary heap and find out if you have the number 4. And then you have to remove this 4 and then you have to do some rearrangement so that the heap invariant and completeness property both are maintained. So this operation is called, this is not dequeuing, but removing a given element, any given element. Right? Number 2, removing any given element. Or any given node essentially. Okay, so how will you do it? So if any element is given, then first of all you do search, right? Search the node, search for the node where means wherever that element, which node is having that element. Then you have to do you have to then remove that node. Let's draw the tree again. Copy from here. Okay. Let's say I'm saying remove. Which one should we remove? Remove 5, for example. Let's say for example, I say remove 5. And what will happen? First of all, it will search the node which is having that particular whatever value or priority index. Then you have reached here. Okay, this one has to be removed, right? So what you do next? You found out the node. So first you have to maintain the completeness property, right? I can't simply remove it and then let the tree arrange itself because then the completeness property will be lost. So to maintain the completeness property, what will I do? Yes.
Replace it with the last node.
Yeah. Take the last node of the heap and then put it here. And this one is gone. Means this one basically moves here. So here 5 is gone, you get 8 here. This one is completely gone. Now you do the rearrangement. What is the rearrangement you have to do? Will you be bubbling up or sinking down?
Sinking down.
Sinking down or bubbling up?
Sinking down because if we want to bubble up, then already the the parents are already less than the last element.
Yeah. So in this case, So basically you will do both. First you will try sinking down, and then you will try bubbling up, both, because you'd never know, this node could be heavier or lighter. It could be light node, right? And in that case it will go up, or it could be heavier node, in that case it will come down. Or if it is none, as in this case, it will just stay there, right? So but you have to run both the operations. When I do sinking down, it will not swap. If I do bubble up, it will not swap. So that's it, I'm done. Right? So that's it. So this is the whole algorithm. So we learned how do we add a new or NQ, and how do we DQ. How do we add an element and how do we remove an element. Now this element could be the DQing thing, or it could be a removal of any random node, any given node. Okay. Does that make sense?
Yes, sir.
Yes, sir.
Okay. Now, in this way, you can implement many algorithms, whatever as per your need. You can define, you can do that. But these were two important algorithms. That's why I discussed with you. And you can see here what is the complexity of both the operations. The complexity of both the operations is yes.
Log n.
Yes, log n. So both addition as well as removal have the complexity log n, which is very efficient as compared to simply maintaining a list of values like in a queue or something. Right? That's why in case of a priority queue, people use this heap. Complete binary heap is a good way to implement the priority queue. Okay, now let's see how do we implement a heap, right? So we saw heap is a very good data structure. It can do many nice things, but how do we implement a heap itself? Because as I told you that the previous implementations, like you define the class, and in the class you define the children, or sorry, in the class you define a node, and node has children. So given a child, you cannot go to the parent, but here you need both. Given a node, I want to know its parents, and I also want to know its children. So that implementation won't work. You can try it out for your own practice and make yourself comfortable with the concept that it is that implementation is not a good, or it is not efficient to implement this heap. Okay, so there are other implementations also available. I will discuss one of those. This implementation is with an array. So implementation of a heap. And when I say heap, I am talking about a complete binary heap with an array. So a simple array how do we implement it in a code with a simple array? So what do we do here? Let's say we have a heap. Let me take it's a very big one. Let's take this one. This is a small one. Let's write the indices 0, 1, 2, 3, 4, 5, 6. And I can implement this with a simple array. say a simple array where the indices are 0, where the indices are 0, 1, 2, 3, 4, 5, 6, right? And the values are 2, 5, 4, 9, 8, 10, and 20. Okay, this is a simple array, an array, and the indices are like this, and these indices match these. So this represents the tree, or sorry, the complete binary heap, right? And you can verify that it is a good representation. Okay, now let's find out, if I tell you for a node, for any general node, for a node n is any number here, from 0 to 6. For any given node, what are the children? Yes, let's say for 2, the children are 5 and 6. But if I give you any number n, a general number n, so what are the indices of the children? If the node index is n, what are the indices of the children? Who can
2n plus 1 and 2n plus 2.
2n plus 1 and 2n plus 2. These are my 2 children. How did you derive it?
Yeah, 2 children is 5 and 6.
Yes. So, but the general formula is 2n plus 1, comma 2n plus 2. So, yeah. Okay. Now for a node n, what are the parents? If I give you this node, what is the index of the parent? What is the index of the parent? Or if I give you the node 6, parent is 2. For 2, the parent is 0. For 4, the parent is 1. For 5, the parent is 2. But I give you any general node n, what is the index of parent?
Floor of n minus 1 by 2.
Floor of n minus 1 by 2. Does everybody agree to this? Let's verify it. If I put 6 here, so 6 minus 1 is 5, 5 upon 2 is 2.5, the floor is 2. So we reach here. Yeah, it works for 6. Let's try something else. Let's say take 2, then 2 minus 1 is 1, 1 upon 2 is half, and the floor is 0. It goes to 0. Yeah. Of course, this will not work for n equal to 0, right? So we have to be careful that n should be greater than 0. If n is equal to 0, then parent is none, right? Root has no parent. Or somebody can say root is the parent of the root, means the parent of 0 is 0 itself. Somebody can define it like that also. So see, in programming, you are defining the world for you. So there is a lot of flexibility. Okay, but of course we follow certain structure so that it is easy to understand and transferable, easy to basically efficient implementation, etc. Some standard practices help always. Okay, so in this way, see, now given any node n, you know the children as well as the parents very efficiently, right? So this is a good representation for a CBH. Now you can write the code to implement the whole thing using this representation, and I think I can give that as an exercise to you. It can be, take it as a practice problem where you implement the whole thing by using this representation. But now this is not the only representation. I can have another representation also. So with this representation, all the operations like polling, which means dequeuing and enqueuing, it becomes very fast, right? But let's say I want to use a heap for some other operation, which is, so okay, tell me what is the complexity of search, or what is the complexity of, let's say I want to search any information. What is the complexity? Search. Oh,
Total number of nodes.
yeah, because you have to find out. If I ask you, if I ask you what is the um, uh, what is the index, what is the, wherever 20 is stored, what is the node index, then you have to search the value 20 in the whole table, and then you will come to the node. Okay, I think this is okay. So search has a of order n. Right? Let's take another scenario in which it's like a priority queue. Let's say when you go to health center, they ask you, they give you a priority. If you are a student, you get a priority 1. If you are a research staff, you get a priority 2. If you are a faculty member, you get a priority 3. If you are a something else, you get a priority 4. Let's say there is a priority index with each. So there are a lot of repetitions also. Let's say you have a lot of repetition. Right? A lot of repetitions are there, but still the priority queue or the complete binary heap property is maintained. Now I want to search for an element very quickly. Then another implementation is with hash functions. This is useful when you have lots of repetition and you want to search for something. Let's say I ask you, okay, I want somebody with the priority 4. Then you have to find out where is 4. So what you do is you maintain a hash table. What is a hash table essentially? It is something like this. You have a value and you have an index. So in this case, let me write down the indices also. 0, 1, 2, 3, 4, 5, 6. So what is the value? Your value is 2, 3, and 4. What are the indices? The indices are, for value 2, your index is 0 and 2, and that's it. For value 3, your indices are 1 and 3 and 6. For value 4, your indices are 4 and 5. Right? This is the representation. Given any value, you know the indices. Now using this, you can quickly find out, if I ask you, oh, tell me a node which has a value 3, which has a priority 3, then quickly you can search up here. For 3, you have indices 1, 3, and 6. Now this can be used in conjunction with your array representation, right? Yeah, but this is the way. This is another representation to, if you want to quickly find out the value, if you want to quickly find out the index given the value. So this is called a hash table.
So sir, we like make these hash tables in programs.
You can, okay, in Python, it's already available as a dict. Right? When you say my some dictionary D is, so you define it like this, 2 2 maps to 0, 2, 3 maps to 136, 4 maps to 4, 5. And then when you will say, what is my D2? It will return you 0, 2. But the problem with this implementation is that if I ask you what is the value at index 2, that becomes costly, right? That's why you also maintain this simultaneously. So you maintain both the things together. Given the index, you can find the value. Given the value, you can find the index, right? So you maintain both these. So maintaining a hash table has an overhead. This is essentially it's called a hash table. So given or implementing a hash table or maintaining a hash table side by side has an overhead that your codes, etc. you have to write extra. But for this particular application, it becomes efficient. So you do it only when you need to search the values. But in general, you may not need this. Okay. So depending on your need, you can make a data structure which is very efficient to do those operations which you need. Of course, implementing all the operations, it's not efficient. It's not worth it. But whatever operations you need, you optimize your data structure for those operations only, right? Okay. So should we stop here now? This was all about heaps. Now, some practice problems will be given to you soon. Maybe in the next class, we can do some practice problems. Okay?
Okay, sir.
Yeah. Thank you very much. See you on.
Sir, good afternoon, sir.
Uh-huh.
Sir, I